Hi, so it's my pleasure to introduce Zeljka Fuchs today. I guess first a brief story. I first became aware of Zeljka's work in 2006 at the Tropical Meteorology meeting when she announced that the MJO moisture mode, Zeljka's laughing, and one of the most senior scientists got up and said this is absolutely not true. And everyone in the audience looked. And 15 years later now, almost 15 years later now, I would say that moisture mode is the dominant way that people think about the MJO in kind of more theoretical circles. So Zeljka was right 15 years ago. And at that point, she was working on her PhD, I believe, or were you a postdoc at that point, Zeljka? I think she was working on her.
I think I just got my PhD. Yeah, just like
okay.
Very fresh.
She went to Croatia for a while and did research there, and was involved in a number of advising graduate students and all sorts of different stuff in Croatia. She eventually decided that she wanted new challenges in the US, and so I guess all along she's been collaborating with people at New Mexico Tech, and so she decided to come back to New Mexico Tech. That's where she also did her PhD, and organize a field campaign, namely the Organization of Tropical East Pacific Convection field campaign, which took place about a year ago. A little bit more than a year ago, and she's going to tell us about her work related to that. And so she's at the Water and Climate Consortium at New Mexico now, which just had the OTREC field campaign. And yeah, with that, I'll let Zeljka give her talk.
Well, thank you, Larissa, for that awesome introduction. I must say that 15 years ago, I was almost crying. But then, you never know in life how a bad experience turns out to be good, because if that senior scientist didn't get up and said what he did, then all of you in the audience wouldn't have known that I said it then, and maybe somebody else would be the one who called the MJO the moisture mode. Okay, so I am going to stop sharing my video and try to share my screen. I've practiced this a couple of times with Pete, so it should work. Okay, Larissa or Pete, can you tell me, do you see the slide?
Yep, it's all good.
Yep.
See the next one?
Yep.
Yep.
All right, testing complete. So, hi everybody. I'm sorry not to be there in person, but today I'm going to talk about the recent field project, Organization of Tropical Eastern Pacific Convection, that took place just about a year ago, and why we happened to be there, what did we discover, and what's the newest science that I have to present. First, I'm going to give you a bit about the motivation behind OTREC, and then I'll tell you how our everyday today looked like, and then we'll complete the talk with the science. So motivation behind OTREC goes as follows. And I figured that we want to build a project, and then we started thinking like, okay, well, if we want to do the field project, what do we want to study and where do we want to study that? And the very first thing that we agreed on was that we want to study convection in as diverse environment as possible, but also at all stages of convection. So those are two important things: as diverse environment as possible, and study convection in all its phases, including the null phase. Because if you always go and fly into the same type of convection, you are more likely to get always the same answer. And so to set up the experiment or the project of diverse environment, and the one that can help us improve our weather models, I guess it just happens, our first thought was Eastern Pacific, because Eastern Pacific area is hard on models. They disagree. And because it also has this very interesting gradient in sea surface temperature meridionally. So I guess I should mention here, I'm showing you the OTREC mean sea surface temperature, latitude and longitude, and these boxes here, B2, B1b, and B1a, are our flight regions. And so how did we decide that those are our flight regions? Eastern Pacific B2 box, because of this strong meridional sea surface temperature gradient. And then once we had that, we were thinking, okay, so what's next? And the B1b box just came naturally to us because it has a very, as you can see, very uniform sea surface temperature in the Southwest Caribbean. So we were thinking this is a nice contrast to B2 to study diverse environment. And then we were collaborating very well with colleagues from Colombia. And they were at the time saying how the rainiest spot on Earth is inland in Colombia, a little bit off the coast. And they have done some extraordinary science at that point, and they have Colombia covered with many radio sound stations, but they never really knew what is going here in the region. And they said, well, what if we knew that? Maybe we could find out that this rainy spot on the planet is not inland, maybe it's right over the ocean. And as it happens, it is very close to this point, Nuki. So B1A was chosen to figure this out. Convection here is interesting because there is this jet that impinges on the coast of Colombia and bringing really amazing storms over there, the Choco jet. And so we said, okay, this looks good, but then what is the other science that we can possibly get from this box? And here came the colleagues who study easterly waves, because there is this school of thought that says that not all easterly waves, that not all hurricanes in East Pacific originate from the easterly waves that come from America across the Caribbean, across into East Pacific, but that perhaps some are initiated, or if not initiated, then intensified by the convection that's coming off the coast of Panama and Colombia. And so that did it, because then if we have a box B1A here and we can observe some kind of formation of easterly wave, and the next day that convection is going to be in B2, because this is how long it takes the easterly wave to pass, about 7 degrees. And then imagine this, if we have an easterly wave that's crossing via Caribbean, the same thing will happen. And so we might catch it here and then the next day in B2. And so here the plan was made to fly on the day 1 B1 pattern, because these two boxes are small enough. It takes you about 2.5 hours to complete the work here. So this is going to be day 1. And then the very next day we will fly B2 box. So we're going to catch interesting convection, and we are perhaps going to catch some easterly waves developing. And just before I move on, I want to point out that we didn't have only the plane operation that I will mostly be talking about, but we had radio sound launches that were stationed here in Nuki. Again, our collaboration with Colombia really paid off. I mean, these guys were launching sondes in incredible weather, not to mention that you can only get to Nuki by boat, and so transportation of equipment was really difficult. But then we also had 2 radio sound stations, one in Limon, here on the east side of Costa Rica, and then one in Santa Cruz on the west side of Costa Rica. And so these stations together with these boxes, we hope, give a nice data for the easterly waves if they are passing through the land. So I guess this is the long answer of why OTREC and why there. Short answer is that, as like I said, Dave Raymond used to be my advisor, and after I spent about 7-8 years in Croatia, I decided that I was a bit bored and needed more challenges, and at the time when life was still normal. We did yoga every Sunday when I was in town, and after yoga we would have beer. And so one Sunday, it just happened that I said I was bored, and they said, let's do a field project, and we talked for hours. And that very day, we basically had the skeleton of OTREC. This is Dave on the left picture, of course. But on the right, I'm showing myself in our G5 plane, and I am holding a quarter. And this is to remind me to tell you a story of how we decided to fly, how we decided when to fly. So as I said, we had a plan where we want to fly, which is very unusual for field projects, because usually field projects go with with all to study a particular phenomena, and then they depend heavily on the weather forecast to decide if that phenomena is going to take place, and then they come up there, and then they maybe decide that this phenomena is happening a little bit further, and so on. So pretty much nobody from the NCAR's G5 crew believed us that we are going to stick to our pattern. But we were saying, no, we know what we are doing. We are always going to fly in the same area in similar pattern, because we want to be able to compare. But how are we going to avoid a bias of always wanting to fly into interesting convection? I mean, we as the scientists are very excited when the storms are happening, etc. And so, what happens if we are just going to get this bias that we can't get rid of, and always end up flying into a similar thing, right? You see some easterly wave developing, let's go. And it's always the same thing. So we came up with this system that we are going to throw a coin, a quarter, and we are going to count heads and tails. And we threw it 5 times and then count 4 and tails, heads, etc. And that would tell us how many days are going to be between our flight pattern, that is saying day 1 be 1, day 2 be 2. So we could have 1, 2, 3, or 4 days in between the flights. However, we also got a very good advice at that point from one of the pilots, Bo, who said, field projects are tricky, as you know, you have done more than one, and you know that things break and things go wrong, so perhaps you can throw out that 4 days in between and try to fly as much as you can. And so we did that, and we were very glad that we did that, because we did run into many problems. So even though in the beginning we were flipping the coin, eventually we flew randomly around all the events that OTREC faced. So it has been completely random and not influenced by weather forecast. So this is where we were. OTREC lasted from August 5 to October 3, 2019. So last year at this time we were already home. Here you are looking at the image of our of Condovac apartments where we stayed, and we were very glad that we stayed there, because some of us stayed there for the whole time. And these apartments had a little kitchen and the living room, and it's really like home away from home. Which is pretty important in the field projects, because you go there and you get so immersed into what you are doing there. I mean, you eat, breathe, and sleep the field project, and you can burn out if you keep eating at the hotel, and if the room that you come into is small. I guess this really helped us, and well, nobody can blame us, right? It's a very beautiful place to work from. On the right, we are seeing the image of this Condovac establishment from the plane. Every time when we were coming back, our pilots tried to fly us over because they thought that was cool, and we also thought that was cool. How did our everyday look like? Well, we partied a lot, and it's really hard to give a Zoom talk and try and make a joke. Yes, we had some team building dinners. We tried to, OTREC was a special project in many ways. One of them was that we had really lots of graduate students, and we also had 4 undergraduate students present, and at any day there were about 20-25 colleagues with us, and I believe that nobody got to leave without catching a flight on the G5. This was one of the things that I fought the NCAR team very hard. I wanted to get as many seats on the plane for the science, because when you're a graduate student, and I know this from the personal experience because my first project was EPIC 2001 when I was a graduate student. When you once see what you're studying, usually with your computer or your paper and a pencil, but when you go up there, and it's different than when you are on a commercial flight, because you are chasing these storms and it's so exciting, and and they tell you we are not trying to avoid weather, we are looking for severe weather. So when we tell you to buckle up, you better buckle up. And of course your adrenaline goes up and you're at the verge of discovering something. And then you spend hours and hours like that in flights and flights, and just the conceptual picture of what you are studying changes and you get new ideas. So on the days when we didn't fly, mostly we planned what's going to happen next, and we dealt with various different issues, but students were the ones who worked very hard on the weather forecast, and then they were trying to see if the weather forecast was correct or not, so they were validating it. And then we tried to meet every day in the afternoon, where they would present what they have worked on. And also, to see who's flying next and who is going to be on duty to launch radiosondes, because that's another thing that the students helped, and we couldn't have done it without them. When the radiosonde launched, we launched at 6 a.m. and 6 p.m. Local time, so fairly early, and you have to start the process much earlier than that. And the graduate students themselves were in charge of that. And I believe that there are 2 online, Miguel and Vijit. I cannot thank you enough for everything you've done. The days that we did fly, we used the Gulfstream V aircraft, and the decision to use that plane was made because Dave and I decided that our main instrument in flight operation are going to be dropsondes. So the dropsondes are the instruments that you throw out of the plane, and they measure temperature, pressure, winds, humidity, etc. as they fall down to the ocean. So they're very similar to radiosondes that our students were launching from the ground with a big balloon. And so in order to sample the whole troposphere, we wanted to fly as high as possible, and this is how G5 came to be, flew at about 13 kilometers. To the left, it's Dave and me, probably after the flight, because we usually try to take off around 6 a.m. local. So the picture on the right is a little bit before that. You see it's still night. The airport opened at 6 a.m., so even if we wanted to, we couldn't fly earlier. The reason for early morning flights was because the convection was developing at that time, and then in the afternoon it was pretty much decaying and not interesting to us. Here's a photo of 3 crazy Croatians. This Stipo, who is on the call too. Stipo was a mission scientist in training, and that meant that he got to be on almost every flight, and by the end of the OTREC project deserved a title of mission scientist, which means you can get to go up on the plane by yourself and decide the science and everything else together with the pilots. And then here is Anna, who was also a student of Dave Raymond at some time, and she went back to Croatia but came down to OTREC just because of OTREC, because she never got to go on the field project like this, and I don't think she regretted it. So as I said, we would start off on the flight days very early. We left the hotel around 3:45, if I didn't forget. Our best friends at that time were the howler monkeys. And so you are seeing here the howler monkeys that were not shy. The picture on the right is actually right in front of my apartment. But you know, they were good friends. I mean, it's 3:45. We're holding our phones, trying to see where we are going. You know, heading towards the cars and then towards the airport. And these howler monkeys are singing us away. That was pretty cool. Then we get to go on and fly. Most of the time when we got there, we always had somebody who was new. So we showed them where the radar is, where the dropsondes are being dropped. They did some kind of a safety briefing, walked around in the plane. The plane mostly has lots of computers in, so we would, you know, start up our satellite images and see one more time if we are doing the right thing by going and flying there. And then for 6 hours, we would be in the air, most of the time, 45 minutes to ferry to our site, and then do work for 4 or 5 hours. And those 4 or 5 hours you basically spend staring at the satellite images, because you need to oversee what's going. You need to kind of guess or get a feeling of what is ahead of you to see if you're going to have to divert or not. And I'll say a little bit more about that just in a second. So OTREC used the Gulfstream V. It managed to perform 22 research flights, which was about as much as we wanted to and as much as we got money for. That amounted to 127 research hours, so that's about 6 hours per flight. And during that period of time, we successfully deployed 648 dropsondes. Those are EVAPS dropsondes, and they're very good. So our efficiency rate was more than 95%. And we had Hiaper Cloud Radar on board of a plane that was looking downward. And we also had a cloud probe that was more the NCAR's instrument than the one we were interested in. But altogether, OTREC didn't just include aircraft operation. It included lots of ground-based operations, and one of them I already mentioned. So those were the radiosondes. Sites we launched from, Santa Cruz and Limon in Costa Rica, and Nuki in Colombia. And then we also had weather and GPS precipitable water network, and collection of rainfall samples all over Costa Rica and Colombia. So it was a pretty big project. One more thing before I get to data, why and how, is I want to stress that more and more field projects and more research that is funded by our government agencies expect you to do outreach. And I, for one, believe that's an amazing thing, and that's why I fought everybody on getting some seats on the plane. But besides that, we managed to do lots of outreach during our time there. To the right, you're seeing an image of the students from Costa Rica University during the open house day that we had. And that was a day in which we got to use a part of the airport in Liberia, where we flew from. We had several talks there, and from that area, the kids got some students, public got some briefing of what to expect next, and then they went down the stairs and came to the plane that was parked right below that gate, got on the plane and got to see what instruments we are using, why and how. Then some things just happened without us organizing. And so to the left is the radiosonde site in Santa Cruz that was right next to the school. And so when the kids saw that something interesting was happening over there, you could not stop them from coming. And they dragged their parents, they came by themselves, they came multiple times. And who knows, you know, maybe one day one of them is going to be a meteorologist and discover something amazing.
Zeljka, we lost your screen. We lost the video from your screen.
Okay, where?
You might want to try.
What's the last slide you showed?
Let me look. I've got it up here too. The last slide was the one, slide 10.
slide 10.
Yeah, if we can't get it to come up again on yours, I'll share it from mine.
Okay. Let's try.
Yep, that's better.
All right. So, but I don't have to talk again.
Right.
You didn't lose the audio.
Right. Nope, you were still there.
Right. Are we seeing this colorful satellite image slide?
Yep.
Okie dokie. So we are looking here at the satellite infrared image of the very first flight that happened during OTREC, August 7. And you see the plane here in our B2 pattern. And I know I said that we were going to fly B1 the day 1 and B2 the day 2. But B2 looks, I mean, not just looks, we knew it's going to be a simpler pattern to fly. So for the very first flight, we chose to fly B2. So this white circle here is Liberia, the that we were taking off from. And then if we were doing the B2 pattern, we went all the way down to southeast and then started climbing up these legs all the way to the end, and then very short ferry home. The blue lines are desired flights, and the black dots represent the desired locations of where to drop the sonde. And so those are spaced degree by degree with a reason, because there is this method called 3D bar that if you have this kind of data, then you can know everything that's happening inside this box. And the day 1 for those who are always excited about convection, it just turned out that we flew through a forming tropical storm Henriette, which at the time of our flight was decaying. And now to the right is our B1A pattern. So if we took off from Liberia, we usually started with the B1A Colombian box and then went up to the Caribbean box. On that day, nothing much was happening here. But here you will see how we had to deviate sometimes because of heavy lightning, strong convection, etc. But you can see that we mostly did what we said. We flew our B2 pattern, we flew the B1A that we extended to the south sometimes, and then we played with the Caribbean box and its orientation a bit. But we were all in those locations, except on one day, and this is to the far west, when we went to fly with the P3 that came from NOAA's HRD, the Hurricane Research Division. They came to fly into a forming tropical storm EVA, and that was really interesting because the models were not definite on whether it's going to develop or not, and these guys, as their everyday job operationally it is to fly into hurricanes, had to make a decision whether to come down or not for about 4 days, and as they have all the permits at ready, unlike us, because when you're organizing a full project, you can imagine you need to get all the permissions to fly into various airspaces, etc. Well, they don't need to have anything like that. So one morning at 4 a.m., they decided to come and they performed their first flight at 9 a.m. So that was pretty cool. But as that day, as they were flying and trying to find the center of EVA, we were flying above them and helping them with our dropsondes. And as I said, we use this method that's called three-dimensional variational analysis, 3D bar. And I'm not going to read through this slide. Maybe lots of you know what it is. But its main goal is basically to tell us what is really happening inside this box based on data that we believe giving us the zeroth order truth. I know lots of us use models and reanalysis, but I am a strong believer in the need for field projects and the real data. So I'm going to briefly show you this before we move into science. The image on the left you've already seen. This is the first day flying through Henriette. And then this is to the right is the mission 20 that took place on September 30. It had this very unusual convection at 4 north that had very strong lightning. So here, this image to the right, bottom right, in red dots are lightning in the past 5 minutes. The blue dots are lightning in the past 10 minutes. So this was a very rapidly developing system at the time, and you would have to be crazy to fly through it. And even if you were that crazy, the pilots would tell you no. So we had to figure out how to deviate around it and how to still keep our dropsondes on the grid so that our 3D bar still works. And so this is the moment in which you then either talk on the headphones with the pilots, or you come and talk to them about the possibilities to do this and that. You can't drop in a turn. There are various constraints that you have, and developing a language that the pilots understand, or the pilots developing the language that scientists understand, that some things are possible and some are not, is an art in its own. But we had an excellent cruise, so I think that was pretty good. On the top, though, I'm showing superimposed to satellite infrared the image from the radar. So this is the reflectivity from the radar, and you can see how Henriette, at the time that convection was decaying, it was very top heavy, whereas our system on September 30 was really just starting to develop. So that was pretty neat. All right, so 22 research flights altogether. Here I'm showing this one joint flight with the HRD flying into P3. So let's say 21 research flights in our boxes B1 and B2. 9 of those were performed in B1 pattern, and 12 were performed in Eastern Pacific. Most of the time it was, as we said, we fly B1 on one day and B2 on the next day. Which brings us back to the part of the talk about the science. But I do hope by now, if you haven't been to a field project, you are saying, I gotta get myself into one of those. And you can ask me about this later, but if you don't, most of the projects nowadays, if you have a fund to come there, we'll be happy to accommodate you and work with you and make you part of the team. So here's the question that Dave and I asked on that one Sunday. How do we study convection? What do we want to study? Okay, yes, diverse environments, and we want to study all the stages of convection. So we're asking the question, what is the environment that convection likes? And this is unlike many scientists who study convection as a series of plumes. Or let's just think about the individual plume, and the plume is evolving in time, and it's developing on this side more than this side, and it's getting this inflow and that outflow, and so they studied the plume and its evolution in time. And I would say that's how most researchers study convection. And so for them, it is very natural to do a field project in which they chase the storm itself. And unfortunately, they most of the time have only one plane. It would be awesome if they had 2 planes, and so they could catch, something happening in the environment before the convection developed there. Unlike them, the question that we ask is, what is the environment that convection likes? Because we believe this is an easier question to answer. You can even think about it like in a statistical sense. What if we can figure out the environment that convection likes? Could we then improve the parameterization of the models and know what is going to happen next? And then if I can convince you that we are not going to chase the plume, but we are going to think about the environment that convection develops in, if it's the environment, the next question is it the boundary layer or the free troposphere? And then there are many scientists who believe that the boundary layer is the most important. There are some who think that it's the free troposphere, and then there are some that think it's both. And so let's try and answer those questions. And to do that, I am going to define vertically integrated moisture conditions to be our proxy for convection. So, you know, higher there is, more convection we have, and then more precipitation we have. And this is calculated from the 3D bar on the dropsondes. And then I'm going to ask, how are some thermodynamic parameters behaving in relation to convection? And those are going to be deep convective inhibition, which is a parameter that basically describes what's happening in the boundary layer. It's defined as the difference between the saturated moist entropy at 1.5 to 2 kilometers, so just the boundary layer, minus the moist entropy within the boundary layer. Then saturation fraction is the precipitable water divided by saturated precipitable water. And the way I think about it is that it's just the amount of moisture that is in our atmospheric column. And then the third parameter that perhaps you haven't heard about as often is called instability index. The way to think about it is low to mid tropospheric moist convective instability. It's a difference between saturated moist entropy at low level, 1 to 3 kilometer, minus the one at 5 to 7 kilometer. And if you're not used to think about saturated moist entropy, maybe think about temperature, and that will help. The relationship between saturation fraction and instability index is known as moisture quasi-equilibrium theory, and it says that this instability index is inversely proportional to saturation fraction. But it doesn't say only that, it also says that there is this Goldilocks cartoon here that Dave and I came up with. If it's too dry or if it's too moist, the convection is not going to be happy, and then there is this just right, the middle part where everything is going to work. And so convection will grow. And just so I can convince you that this relationship between instability index and saturation fraction holds, this is a scatter plot between the two for the OTREC data. And this is one of the first plots we made after we finished OTREC. Each of these dots represent one dropsonde. Red is our Colombian box, blue Caribbean box, and black Eastern Pacific box. And those are only for the areas in which we had convection. So all the ones without convection are not here. And you can see that there is a very nice correlation between the two. You might notice some outliners here, and all these three in the Colombian box belong to one flight, and we're still trying to figure out why are they, you know, outside this line that you can eyeball that the rest of the data has. And then we're going to look at one more thing, and that's the vertical mass flux profiles. Vertical mass flux profile defined as rho times vertical velocity horizontally averaged, but then also the mass flux index, which is the difference between the mass flux averaged at 7 to 9 kilometers, so that's the one we call high, and low 3 to 5 kilometers. And you can think about it as a measure of top heaviness of convection. So if it's positive, that means we have high vertical mass flux profile. And another plot from that first paper that we published on OTREC is showing various vertical mass flux profiles for the convective events during OTREC. We have Eastern Pacific, Colombian, Caribbean, and Caribbean seems to be the least interesting. It pretty much always looked the same, but we also didn't have the opportunity to fly into many convective events there. The Colombian box, we had more luck, and of course Eastern Pacific. And I don't want to go into this much. I just want to tell you that the solid here show the developing convective systems, and the dashed lines show the decaying ones. And so as expected, we see the top-heavy profiles connected to the decaying ones, and the more bottom or deep ones with the developing events. Okay, so after we've done this work, I kind of asked the question, well, okay, so we know all this, but we still haven't answered, is the convection different in different environments? Does it depend on sea surface temperature? Does it depend on the proximity to land? Does it depend on different latitude while still in the tropics? And then I spent, I think, months, not weeks, months, staring at each individual OTREC mission divided by hour boxes, and I looked at everything that I could think of, and I just couldn't come to any conclusions. And then I decided, well, this is pointless. Maybe not ready for this yet, or maybe this is not the way to look at it. Why don't we do the systematic analysis without any, preconceptual hypothesis or whatnot? Let's just see what OTREC can tell us when it comes to convection and environment. And then we threw in the predict data to that as well, because predict deployed many dropsondes. So predict took place in 2010, and they deployed 547 dropsondes in this area of Western Atlantic and the Caribbean. So like a really big area that they covered. These yellow dots represent the dropsondes. Their main goal was to study development of tropical storms. So they mainly flew into convection, but still, that's good data. So we decided to look at the systematic analysis from OTREC predict and see what do we get. So what I'm showing you here is this little cheat sheet here, is so you remember B2 is our Eastern Pacific SST gradient box. In red is our Colombian box. In blue is our Caribbean box. And then in green is the data predict. And predict is different from OTREC in the sense that it flew, first of all, they flew in higher latitudes, but also they had higher SST. So the very first thing that we looked at was, how does convection relate to sea surface temperature? Is it, are there any sea surface temperatures that it particularly likes? And we came up with this plot that, in my opinion, says, except maybe here at the very lowest SSTs, that convection really doesn't care about SST, it cares about something else. I mean, it may be different for different SSTs, but whether there will be convection there or not is not going to depend on it. Then the next, we are looking at saturation fraction as a function of SST. And here you see like maybe 301 Kelvin. We can see that it really doesn't care, but then there is this saturation fraction drop that happens, and this is because when the SST is higher, convection can still exist for lower values of saturation fraction. And then the instability index, when we look at the function of SST, shows that we will have higher values of instability index at higher sea surface temperatures. And that shouldn't come as a surprise, because the instability index is defined as the difference between the two temperatures at low and mid-level. And then this scene, as a function of SST, I don't think there is really anything much we can say here except these blue dots up here that basically represent inversion. So lower the D scene, more convection will have, because it's D scene is deep convective inhibition, so it's not going to have the inhibition. So I would say it doesn't really depend on SST. Whereas the mass flux index, which, remember, if it's positive, it's top heavy. I would say that our OTREC and predict data show that higher SSTs you have, more top-heavy vertical mass flux profiles you have, and I'm pretty sure that Larissa would agree with me on that one. So after we looked at that, then we looked at, well, okay, so when we look at all our boxes, what does our convection depend on? And so we are looking here at the relationship between convection and saturation fraction, convection and instability index, and convection and D scene. And it is pretty scattered because it includes all the situations of different stages of convection from null to strong. And I should mention here that every dot here represents 1 by 1 degree on which 3D bar was performed. So it's not anymore that every dot represents every dropsonde, but this has been the 3D bar. So I'm not much into this because I'm running out of time, but I want to show you how once when we saw that and we saw that there is a relationship between those, we said, okay, but it's so scattered and it's not saying us if convection is any different depending on the area or depending on the strength. And so I decided to divide convection on all the way to the right, very strong convection. So we're looking here at the saturation fraction versus instability index and saturation fraction versus this scene. We are expecting to see intercorrelation here. We're expecting to see moisture quasi-equilibrium here, and we are also expecting to see high saturation fraction at the low D scene. But what we are really trying to see is how are they different depending on the location where we are, right? We have uniform sea surface temperature or not, and well, you can judge for yourself, but other than the fact that saturation fraction can be lower for higher SSTs, which is reflected here, I can't really tell that it is much different. Then to the left of that, we're looking at the weak to medium convection, which shows a similar thing, just more scattered. And then we are looking at the null to weak convection, which is showing a big mess, which we are still looking into. But what is interesting to me, yeah, and all the way to the left is all cases. But what's interesting to me from this picture is to say that it seems that when you have a strong convection, the differences are much smaller than when you have, the differences in the environment are much smaller among different regions than when you have a weak convection. Then I wanted to show you what the vertical mass flux profiles look like for those cases when we have strong convection. So green is predict and black is the Caribbean box. So you see how the mass flux profile is very deep. The Caribbean is, the values are smaller because, as I said, we didn't really encounter that much convection when we flew in the Caribbean. So that might be the reason. But what's interesting is to look at the Eastern Pacific, blue, pre-bottom heavy, and then B1A, the Colombian box, also bottom heavy, but with the maximum a little bit higher. So that's at least one of the differences that we can see for strong convection between those two regions. And I'm almost done. After looking at all of that, the question was, okay, so this is awesome, right? I mean, systematically looking at everything, we do know that convection depends on high saturation fraction, low instability index, and low D scene. But what happens first, and you know, is it the saturation fraction, is it the instability index, is it D scene, is it something else? Can we look at the time evolution of convection? And the answer is, well, no, we cannot, because we flew only one plane, performed the 3D bar, which gives you like a snapshot of what's happening in that box, but it doesn't give you the time evolution. So we decided to look at the ECMWF analysis. So this is from ERA 5. I'm showing you here, averaged over all individual cases that had the moisture convergence greater than 1 from OTREC. And then going back to EC and fishing out all those cases and plotting them as a function of time. So on x-axis, you're looking at time in UTC. So remember, some of you don't know, but 6 a.m. local was 12 or noon UTC. So this line here represents when we started flying, and this one represents when we stopped flying. So this is reanalysis, which means that our dropsondes have been simulated into their analysis. And we are looking at here at the moisture convergence. So nothing much over the night, and then very, very, very early in the morning, things start developing and reaching the maximum of convection up here around 16, 17 UTC, which is 11 a.m. when we were finishing our flight. Saturation fraction shows to increase very nicely, actually, following the moisture convergence. Instability index, I don't know what is really this peak here. It's a similar one in this scene, but just when you look at the values, if you know how the instability index are, this is not much of a difference. But the general trend is that it's decaying, as is this scene. And saturation fraction reaches maximum, and instability index reaches minimum, and this scene reaches minimum at the same time as the moisture convergence does. So it appears as they're all acting simultaneously at the same time, and we can't really say which one happened first. But then this is very interesting. So I remember the MJO and everything that I have thought about the MJO, and the moisture mode was just the first part of the puzzle, and the next one were the surface fluxes. So I said, well, why don't we look at the surface fluxes, surface light and heat fluxes, and see if they maybe act before all of that happens by moistening the troposphere. And sure enough, this is what we got. So prior to all the increases, decreasing, and whatnot, it appears as we have surface fluxes that are moistening the atmosphere, and once when their job is done, they fall down, they decrease. Now, I'm very excited about this plot because maybe it's giving us an answer on what was there in the beginning. However, as somebody who's advocating for field projects and the value of the data, I can't help myself but ask a question of, can we trust this analysis? So what we've done is show on this plot the solid red lines represent still the same thing, but the dashed lines, the red dashed line represents the operational run from ECMWF model with dropsondes simulated in the run, and the blue dashed line is without dropsondes. So we have a colleague in Reading who managed to run their operational model by initiating it at 12 and including dropsondes and not including dropsondes to see what's the difference. And so my interpretation is that when it comes to moisture convergence, I mean the red dashed line follows very nicely the ERA 5. But when there are no dropsondes, then it seems that the model is going to underestimate the moisture convergence. The saturation fraction, in my opinion, they are very similar. I don't know why ERA 5 is getting a little bit higher value, but keep in mind the saturation fraction between 0.8 and 0.85, so the difference is not very big. The instability index, they almost match. This scene, they almost match. And for the surface fluxes, they're very similar. Now, I don't know what happened before UTC because I can't perform the run with and without dropsondes for before. But I am hoping, and I'm very excited to hear your comments, I'm hoping that this 6-hour window, what it showed for the analysis with and without dropsondes, can at least tell us that we, at least when it comes to trend of minimums and maximums and the timing, it is okay to trust ERA 5 for this particular analysis. We have seen some other things when it's harder to believe it. So to conclude, I would say that convection depends on saturation fraction, instability index, and this scene. And if I had the question in the beginning, boundary layer versus free troposphere, that means both. Convection appears to be similar in all the regions that we have looked at. And the final thought, the surface flux is responsible for the convection. And thank you also very much. I want to thank everybody who participated in OTREC. I want to thank Larissa and Miguel and Vijit. It was really awesome and a great honor to work with you. And I want to say that all the OTREC data is publicly available at this webpage. And if you can't do it down and you're interested, just shoot me an email and I'll send it to you. Thank you very much.
Thank you, Zeljka. I think there's a way we can clap if you remember how to find the clap emoji. Yeah, I'll open things up to student questions. If any of the students have questions, let's start with that.
Did I stop before that? Did I stop sharing the video? I mean, my...
You're still sharing your screen.
I am. Do you want me to stop?
Either way. Zoe has a question. Looks like.
Hi. Okay, so I'm Zoe's roommate, Juliet, and we live together. I'm a grad student. And great talk. This was really cool. I was just curious if you could perhaps comment a little bit on the potential influence that the diurnal cycle could have on observing the vertical or the bottom versus top heavy vertical motion profiles. Like if you think that you would be getting significant differences in what those profiles look like if you flew over at different times.
Yeah, that's a great question, Zoe, and unfortunately I cannot comment. That is one of the downsides of OTREC. We just didn't know how to get around that. So when it comes to diurnal cycle, our data, unfortunately, is limited.
Sure, thank you very much. Thanks again.
Thank you.
Looks like Miguel has a question. Do you want to go ahead? Yeah.
Wondering if you could comment on what you think the role of moisture storage might be, and using moisture convergence as your variable, you sort of have to assume that moisture storage is negligible, but is that true on the timescales we were observing for OTREC?
I'm not sure if I understand the question completely. I mean, you know, when you think about what's going to be proxy for convection, nothing is ever going to be perfect, right? And there was no way for us to collect the rainfall to get the precip over the ocean. So I don't know if vertically integrated moisture convergence is really something that you can 100% get on board and say that's a proxy for convection. But I think that's the best we have. Like I used to think that we can maybe think about saturation fraction as proxy for convection, and if all these plots are correct, maybe you can, right? It's just the thing that saturation fraction also influences the convection. So when you start using it as convection, you get one parameter less.
Thank you.
So anybody wants to go on a field project?
Bet so. I bet everyone does. Looks like Deepo has a question.
Yes, I'd like to go on the project.
Yeah, I want to go again.
So Zeljka, you saw a little bit different relationships between instability index and I guess it was saturation fraction for the different plots, subplots that you had. There was a picture with, I guess, 8 different subplots, all cases.
Yeah, so it had strong convection, medium, and weak. Yeah.
So that was the amount of moisture convergence that you were.
So based on the moisture convergence, I divided the convection to be strong, weak to medium, and null to weak.
Yeah. So it seemed like you saw the strongest relationship between instability index and saturation fraction for the strong convection. Is that right?
Yes. Yes.
Yeah.
And I mean, but that's what we would expect. What I thought they're going to have certain different slopes. You know, I thought there will be more difference depending on the region where we are. In particular, I thought there will be more difference between predict region and, I don't know, the south part of B2 box. But when it comes to strong convection, it seems that my conclusion is that when this convection is strong, it looks pretty much the same, at least if you're looking at these parameters, right? Now, the devil is in the details, though.
Yeah.
You know, I'm not claiming that this is a full picture at all. I just got so frustrated in figuring out the details when I was looking at each specific flight that I decided I'm going to do this systematic analysis to at least get, you know, myself something that I know it is, and then I can deviate from that and say, aha, this was different, and maybe we can figure out why.
Thank you. Any other questions? I guess I'd like to open it up to general questions. So faculty can ask questions at this point too. I guess I asked a question. There's a couple of you out there. If there's, sounds like Juliet or Zoe has another question.
Hi, this is actually Zoe this time. I was curious if you did any comparisons. I know you were using ECMWF to compare your model observations or the assimilated data. Have you done any comparison with like GFS or other data that goes over that area?
That's a good question. No, and the reason for that, well, we could. I mean, why not? But the reason why we didn't is because we have collaboration with Peter Bechtold from ECMWF, and I don't have a collaboration like that with GFS. I don't have anybody who would do the run for me with and without the dropsondes.
Okay.
But you know, it would be interesting to see if they show the same stuff as ERA 5 does.
All right. Thank you.
Thank you.
Okay, there's a question in the chat from Angel. He says, have you looked at the potential role of horizontal moisture advection? And in parentheses, he says also he'd like to do field work.
Yeah, no, we didn't, right, Stipa?
No.
And I don't know. I don't know. Our group is not big on looking at the moisture advection, which, I mean, this is a good question. We should look at it. I do know when it comes to advection, though, that trusting the EC, that would be like one segment where I don't know if I would trust the EC, because the EC doesn't get winds right, especially in the Eastern Pacific. And I think that, for instance, the moisture vertically integrated moisture convergence difference between dropsondes in the model and dropsondes not in the model is because of that. So yeah, good question. We can think about it. Oh, sorry, I don't hear you, Larissa.
I'm on mute. Okay.
Okay.
Thanks. Has said thanks. And I'm not seeing any more questions. So if there's no more questions, let's thank Zeljka again. Zeljka also goes by Z since her name is complicated. So let's thank Z. And yeah, thank you very much.
Thank you all, and I hope to see you in person one day.